Good evening, students. Today we shall see about power meter and VSWR meter. So these meters we have used in our lab experiments for measuring the power and VSWR. So basically, the power meter is used to measure the average power, and VSWR is used to measure the standing wave ratio. So power meter, in the sense, it is classified into three types. That is low power meter, high power meter, and medium power meter. Similarly, VSWR meter is classified into low VSWR meter and high VSWR meter. So first we shall see about the power meter. So in power meter, as I said earlier, we are measuring the average power. So the average power is the quantity of energy dissipated or stored per unit time. So the average power is measured using the formula, that is peak power multiplied by the duty cycle. So how we are considering the low power, medium power, and high power means the 0.01 milliwatts to 10 milliwatts power is considered as low power. We are dealing only about the microwave power, not the other powers. Okay. So first, for measuring the low power, we are using the bolometer technique. In bolometer, what we will do is, first we will use a power sensor in the transmission line of microwave. So if a RF microwave power is transmitted through a medium, that is a waveguide, what we will do is, along the transmission medium, we will keep the power sensor. So that what that power sensor will do is, that power sensor will detect the RF power, and then it get measured using some principle. In low power, it uses bolometer, and in high power, it uses certain other techniques. So based on these techniques, the power can be measured. So before measuring the power, the RF power to the sensor is turned to be 0, as well as the power input to the sensor needs to be 0. So this process is known as 0 setting. Only after setting these settings to 0, then only we need to start the measurement. So first, after doing the 0 setting, what we are going to do is, then the RF power is turned on, so that our RF power meter will show some value from 0 to 10. That is how we will measure the low power. So first, the basic thing what we need to do is 0 setting, and after 0 setting, the measurements can be done properly. So then we can see the basic circuit diagram of a bolometer. So based on bolometer only, we are measuring the low power. So we know that bolometer is a device that is used for low microwave power measurements. The element used in bolometer can be either positive temperature coefficient or negative temperature coefficient. The positive temperature coefficient device is known as barator, and as you know that the resistance increases with the increase in temperature. So then we know that there is a negative temperature coefficient device, that is thermistor, in which the resistance decreases with increase in temperature. So the bolometer used in the low power measurement, we either use this barator or thermistor. So it detects the change in resistance, and based on that, we can easily measure the microwave power applied to the device. So in this, we can see a place where microwave power is hitting into the circuit. So after the microwave hits into the circuit, so before microwave power inputs to the device, what will happen is, we will what we will do is, actually this is a bridge circuit. We need to balance the bridge. So before the microwave power gets hit into this device, the bridge is the bridge is balanced. So once we are inputting a microwave power into the circuit, what will happen is our bridge gets unbalanced. So that unbalanced current is measured using this ammeter, and so from that current we can easily measure the input power. This is how we will measure the low power. So in measurement of low power, we will have two types of circuits, that is single bridge bolometer and dual bridge bolometer. So in single bridge bolometer, what we are doing is, first we will balance the bridge. So using this variable resistance and variable power supply, and once the bridge is balanced, what we will do is, we will expose the microwave power into that thermistor. So what will happen once the power reaches the thermistor, the resistance will vary based on that variable resistance. How the resistance is varied, the voltmeter reading is denoted. So we know that from voltmeter reading, we can easily calibrate those readings into the power meter. So for that, what we are doing is, under the balanced condition, the voltage measured using this circuit is denoted as E1, and after exposing the circuit into the microwave power, we will measure the voltmeter reading as E2, or V1, V2. So actually, the power of our incident microwave can be measured using the difference between our E1 and E2. So E1 is the voltage of the bolometer under zero microwave condition, and E2 is the voltage of the bolometer under RF microwave, after the RF microwave incident. So this difference in E1 and E2 will give us the incident RF power. So the disadvantage of using a single bolometer bridge circuit is, generally it is very sensitive to the room temperature, that is ambient temperature. So that many false readings will happen. So to avoid these false readings, we are moving to dual bridge bolometer. So in dual bridge bolometer, as you can see in this circuit, the top portion of the bridge has, the top portion of the bridge measures the input microwave power, and the bottom portion, that is the second bolometer bridge circuit, is used to adjust the effects that cause due to the ambient temperature. So if there is any temperature variation inside the room where we are taking the measurements, using the second bridge, we can cancel those effects of room temperature or ambient temperature. So when we are incidenting any RF microwave power, what will happen is, it is getting incident into the first bridge circuit. So if we are incidenting any RF microwave power, the output signal will be E2 by 2. If there is no input RF power, the output will be E1 by 2. So based on this, we can measure the average input power, that is E1 squared by 4R, using this E1 minus E2 multiplied by E1 plus E2 divided by 4R. This R is the resistance value that is taken from the bridge circuit. So if there is any change in temperature, we can use this second formula, that is same as the first one, and we can easily find the power that is incident using the radio frequency wave. So this type of circuits are used only for low power measurements. So then we are having medium power measurements. So in RF and microwave, 10 milliwatts to 1 watts is considered as medium power. So how we are going to measure this medium power is, generally we will introduce a special load on the path of propagation of microwave. So the power is measured, which is proportional to the change in temperature of the load. So before, in low power, what we have done is, based on the change in resistance, there will be some change in the voltage. So based on tracking the voltage, what we have measured the power. So in medium power, what we are doing is, we are introducing a special load in the transmission medium, and based on the temperature variations, we are trying to measure the medium power. A same principle is applied for high power also. So here the bridge balance technique is used. So in medium power, we are using the calorimeter method. So the heat transfer based on calorimeter is used for medium power, and the measurement of high power, that is 10 watts to 50 kilowatts. This this is very high power, and this power is mentioned as very high power, and this high power is measured using calorimeter as well as watts meter. So the medium power is measured only using calorimetric technique, but these high powers are measured using calorimetric as well as watt meters. So this high power measurements may be dry or flow type. In dry type, what we are doing is, we are filling the coaxial cable used in the measurement with a dielectric of high hysteresis loss. And in the flow type, we can use some water or oil or some liquid that is a good absorber of microwaves. So this is how we can measure the things. So first we can see about static calorimeter method. So in the diagram we can easily see that in the middle part there is some slashed lines. So these slashed lines are the dielectric material with some hysteresis loss. So if without RF power, there is a specified temperature based on the material, dielectric material used in the cable. So after some RF power is incident into the cable, what will happen is the temperature will get increased. Since our RF power is somewhat medium to high level, so due to the temperature inside, that is composed inside the RF and microwaves, the whole circuit gets heated and the temperature difference is noted. So before incidenting the RF power, we will have some temperature. After incidenting the RF power, we will have some other temperature. So by taking this difference, we can easily find the power, that is medium power. So the average power, as I said earlier, we are measuring only the average power. So the average power is measured using this formula: P is equal to 4.187 m CPT T watts. That m is the mass of the medium that is used. Cp is the specific heat. T is the rising temperature before RF power is applied and after the RF power is applied. T is the time difference between these two processes. So one more thing is, the load is generally isolated from the surrounding. So that due to the ambient temperature and room temperature, there will be no difference in the medium power readings. So the second type is, we are using the circular calorimeter method. So here what we are doing is, generally we will use two pumps, that is one inlet pump and one outlet pump. So through the inlet pump, the water is allowed to flow through the outlet pump. So before applying the microwave, we will have a specific temperature of water that is measured. Then while the water is moving on, in the middle of the place, Similarly, this inlet temperature and outlet temperature. In between those inlet and outlet temperature, what we will do is we will incident the medium microwave power input, microwave waves. So what will happen once these microwaves will incident into the bath of water, the temperature of water will gets increased due to the heat composed within the microwaves. So that first without microwaves we have took some reading, and with microwave we have took some reading. So based on the difference between the two readings, we can easily find the average power. This average power is found based on this formula, that is P is equal to this long formula 4.187 VDCP T2 minus T1. V is the rate of flow of the fluid. I said as water, we can use oil or some other fluids based on our requirements. D is the specific gravity of the fluid. T1 is the inlet temperature and T2 is the outlet temperature. So based on this formula, we can easily find the medium power. So then, as I said earlier, for high power, we are using the calorimeter as well as watts meter. That's the only addition. This calorimeter, watt meter is used in high power measurements. So here we can see that in the top of the circuit, we are having a 1200 cycles per second generator. So generally this is considered as a standard value. So before applying any microwaves into the circuit has a values of 1200 cycles per second. So in the left hand side we can see that input. So in that input side we will apply the RF microwaves into the circuit. So what will happen, as I said earlier, if we are applying a high power microwave into the circuit, it will cause some heat in the circuit due to the heat dissipation. So next to the input we can see that there is an input load. So what if RF waves are incident into the circuit, the waves will make this resistance, the temperature of the resistance to increase. So when the input load resistance gets increased, that input temperature gauge, which is proportional to that resistor, is gets increased. So as I said earlier, before applying this, actually this bridge is balanced, that is in 1200 cycles per second. So due to this input RF microwave temperature disturbance in input temperature gauge, the whole bridge gets gets unbalanced. So unbalanced means there is some temperature difference. Basically, by using 1200 cycles per second, there is a specified temperature. After applying the input to the load and that heat got dissipated into the input temperature gauge, some temperature change that happens inside the circuit. So that temperature difference is measured by the comparison temperature gauge at the right hand side. So the temperature difference in the comparison temperature gauge is then dissipated to the comparison load, and from the comparison load and comparison temperature gauge, the values are amplified and it is measured using this watts meter, that is power meter. So this is how we will measure the high power microwaves using calorimeter watt meter technique. So for medium power we will use only the calorimeter technique. For high power we will use both calorimeter and watt meter technique. So here the temperature difference is due to the unbalance in the bridge. So then we shall move on to the VSWR meter. VSWR means voltage standing waves ratio. So it's a very important measurement, since how these VSWR gets generated, that is standing wave ratio. Generally, if there is any impedance mismatch between the source and load. Some waves are getting reflected instead of passing from source to load. If we are sending the waves from source to load, due to the impedance mismatch at the load side, some waves gets reflected from load to the source. But these reflected waves are not good for our transmission, and we need to we need to minimize those reflections. So, but it's very difficult to minimize those reflections. So, for that purpose, we are using this VSWR meter. In our lab also, we have used this VSWR meter. So, this is the general diagram of VSWR meter, how we will use VSWR meter in a circuit. 1 kilohertz wave is generated and microwave signal gets multiplied with that circuit, and then it's amplified. This circuit is similar to that of the modulation, and that modulated wave is transmitted through the waveguide and is detected by the detector. And by detecting, what the detector will do is, the detector will detect the maximum voltage and minimum voltage. So we know that VSWR is the ratio of maximum voltage and minimum voltage. So based on this, by knowing the values of Vmax and Vminimum, we can easily measure the VSWR values. Okay. In VSWR, we are having two things, that is low VSWR and high VSWR. We have used both this low VSWR and high VSWR in our lab sessions. So low VSWR in the sense the S is VSWR S is less than 10. High VSWR in the sense S is greater than 10. So if S is less than 10, here we can see the Klystron power supply, mount tube, isolator, attenuator, frequency meter, slotted line section, VSWR meter, and load. So by adjusting the slotted section, I hope you remember the experiment. By adjusting the slotted line sections, we can find the value of Vmax and Vminimum. So from that, Vmax by Vminimum will give you the VSWR value. So finding the low VSWR value is somewhat simple, and then measuring high VSWR. So high VSWR in the sense S value is greater than 10. It uses a concept known as double minimum method. Why we are going for double minimum method for high VSWR circuits means the value of the V minimum is very small compared to the V max. It's very difficult to measure the V minimum since it's very small. So instead of measuring the V max and V minimum, we are using this double minimum method. So double minimum method, what we will do is, we will move the slotted line from the source to load, and we will tune our output device. Generally, we will use CRO, and will find the place where the maximum, and we will find the maximum, and we will find the maximum value. So while moving the slotted section, after some distance, we will find that maximum and minimum point once again. We will note that distance. So I think we have used this vernier caliper for this measurement. So by using this double minimum method, we can find the value of VSWR by using the formula lambda g divided by pi into D2 minus D1. D1 and D2 are the places where we are getting the minima. D1 is the first minima, and D2 is the place where we are getting the second minima. So lambda g is the guided wavelength, and it's found by using this VSWR value. So in today's session, we have seen about the power meter and VSWR meter. I hope you have understood all the things. And any doubts? Doubts? Oh, do you have any doubts?
No, sir.
Okay, thank you. So we will have a specific doubt clarifying sessions in the coming week. I think the 15 is very easy, so we can have a separate session. Thank you all. Stay safe.